This is the 14th video in a series devoted to differential equations, and recently we've been working our way through the solution techniques for linear second-order differential equations, and we're going to look at another one today. And so in this setup, we suppose that we already have a fundamental set of solutions, which we'll call y1, y2, to the following homogeneous equation. So we've got p0x y double prime plus p1x y prime plus p2x y equals 0. So the 0 here is what makes it a homogeneous equation. And then we're going to use our solution y1 and y2 to find a particular solution to the same differential equation where we have included a forcing function. So we've got p0 y double prime plus p1 y prime plus p2 y equals f of x, where that f of x is a general forcing function. Now, before we get started, I'd like to point out that this method is generally known as the variation of parameters. And unlike our previous methods that we've looked at that involved reduction of order or maybe undetermined coefficients, this one is a little bit more general. And in fact, what we can do is, since we know y1 and y2, we can build a general solution strategy. So this will work for any f here and any differential equation. Now compare that to what we had with the method of undetermined coefficients, which only worked for differential equations like this where we had constant coefficients and a small family of forcing functions involving sines, cosines, exponential functions, and polynomials. Okay, so let's get into our building or our construction of this general solution. Okay, so let's suppose we have a particular solution, and by a particular solution I mean a solution to this purple boxed equation, and I'll call it y prime. And we're going to suppose two things. One is that it is of the form z1 times y1 plus z2 times y2. So there are these function combinations of y1 and y2 where those are our solutions to the homogeneous equation. And z1, z2 are some functions to be determined. Now, in addition, we're going to assume that z1, z2, y1, and y2 satisfy a certain condition. And that condition is that z1 prime times y1 plus z2 prime times y2 equals 0. So I'll just put an also here. That's another thing that we are assuming. Okay, so now that we've got this written down, let's maybe go ahead and take some derivatives here. Obviously, we want to take some derivatives of yp and plug it into our purple boxed equation because we're assuming that it's a solution to that. And what we want to do is build some conditions on z1 and z2. Okay, so anyway, let's take the first derivative, yp prime. We'll have to use the product rule here. So we have z1 prime y1 plus z1 y1 prime. So that's from the first term. And then we'll have z2 prime y2 plus z2 times y2 prime. Okay. But notice this like funny looking assumption that we made actually has a simplifying effect on this derivative. So I'll overline the things in orange that sum to this condition that we have imposed. So that means we can take these two terms and just get rid of them because they add to 0. They're not 0 by themselves, but they add to 0. So let's see. That means yp prime actually can be written as z1 y1 prime plus z2 y2 prime. Okay, great. And now let's calculate yp double prime as well. Okay, so we'll have to use the product rule again. And in this case, we'll split these two terms into two more terms, giving us 4 total terms. So we'll have z1 prime y1 prime plus z1 y1 double prime from taking the derivative of this first term plus z2 prime y2 prime plus z2 y2 double prime. from taking the derivative of this second term. Okay, so let's maybe box these so we have them to work with later. So just to reiterate, we've got yp prime is this sum, yp double prime is this next sum of 4 terms, and our original yp is this sum of 2 terms up here. Okay, so now we'll plug this yp double prime, this yp prime, and this yp into our purple boxed equation. Recall that yp was supposed to be a solution to this purple boxed equation. So we know if we plug that into the left-hand side, we get the forcing function out here on the right-hand side. Another thing that I'll do is I'll collect some terms. I'll collect z1 terms, z2 terms, and then all of the other terms like on their own. So let's maybe overline in blue z1 terms. So that'll be like this one right here. So there's my z1 term from yp double prime. I have a z1 term here from yp prime, and then a z1 term here from yp. And then maybe in orange, I'll overline my z2 terms. So here I have a z2 term from yp double prime. I have a z2 term from yp prime. And then I have a z2 term from yp. And then finally in red, I'll overline everything else, which does not involve a plain old y1 and a plain old y2. It involves their derivatives. Okay, so now putting yp into our purple boxed equation and then doing that collection will give us the following. So I'll factor a z1 out of everything I can, and then I'll use blue parentheses to collect everything else. So we'll have p0 times y1 double prime. Recall that yp double prime is multiplied by this function p0. And then I'll have plus p1 y1 prime plus p2 times y1. And let's close those blue parentheses. And again, those all come from the blue overlines. Now let's do the same thing with the z2 terms. So we can get that in these orange parentheses just to color code this. And we're going to have essentially the same thing except for y2s instead of y1s. So we'll have p0 y2 double prime plus p1 y2 prime plus p2 y2. And let's close those parentheses. Great. And now let's see, everything that's left over only comes from yp double prime. But let's notice yp double prime is multiplied by p0. So I can put a plus p0 here and then use my red parentheses to have z1 prime y1 prime plus z2 prime y2 prime. And let's close those red parentheses and note that we've got an f over on the right-hand side. Again, because we've got a particular solution to our equation right here. Okay, so next up, let's recall that y1 and y2 are solutions to this associated homogeneous equation. So that means that everything in these blue and orange parentheses ends up being 0 because they're exactly the differential operator over here on the left-hand side being evaluated at y1 and y2. And being a solution means that you satisfy this equation. So anyway, we've got 0 right there, and then this also condenses down to 0. But then that allows us to easily solve for this stuff in the red parentheses. So we've got z1 prime times y1 prime plus z2 prime times y2 prime equals f of x over p0 of x. I'll put my dependence on x back in just to recall that those are functions. Okay, now we're going to move to the next board to finish our derivation of the solution strategy, but I'd like to point out that we have this equation satisfied, which only involves z1 and y1 and first derivatives. And we also have this equation right here satisfied that only involves first derivatives of z1 and z2 as well. So we'll start on the next board with those two equations and see what we can do. So this is where we ended the last board. We suppose that if yp was a particular solution to our purple box differential equation of the form z1 y1 plus z2, y2, satisfying this first equation, then it must satisfy this second equation. But notice we've got a system of equations for z1 prime, z2 prime. Recall that z1 and z2 are the unknown functions, whereas y1 and y2 and f and p0 are known functions. Recall that we know the solutions to this homogeneous equation, so we know what those are. Maybe they're like e to the x times sine x, or maybe they're like 1 over x, or something like that. The point is we know what those functions are. Okay, but what's our favorite way of solving like a general system of equations? Well, maybe we'll put it into matrix form. So notice that this is equivalent to the following matrix equation. We can write this as y1, y2, y1 prime, y2 prime times the vector made up of z1 prime, z2 prime equals the vector 0 and then f of x over p0 of x. Great, so that's just translating those two linear equations, well really linear in z1 prime and z2 prime, into this matrix vector equation. But let's recall that if this is a fundamental set of solutions, then that means that they are linearly independent. But if they're linearly independent, then the Wronskian is non-zero, but the Wronskian is exactly the determinant of this matrix. So since the determinant of this matrix is non-zero, that means it has an inverse. So we can multiply by the inverse. There's a little bit more going on. This actually means that the Wronskian is never zero. We proved something like that in a previous video. So anyway, what we can do is have z1 prime, z2 prime. That vector is in fact equal to the inverse of this matrix. So red column wise, y1, y1 prime, and y2, y2 prime inverse times this vector f of x over p0 of x in the second entry and 0 in the first entry. Okay, so now let's maybe recall over here in this orange box how to find an inverse of this 2 by 2 matrix. So maybe I'll write it down in general and then we'll apply it here. So this is from a standard linear algebra class. So let's say we have a matrix made up of A, B, C, D. Then there's a nice formula for the inverse of a 2 by 2 matrix. It's not so nice if you go to larger matrices though. Okay, so this is 1 over the determinant, so 1 over AD minus BC, and then we swap the diagonals, so that means we have DA on the diagonals instead of AD, and then we negate the off diagonals. So we have negative B, negative C, like that. Okay, so that means we can rewrite this as 1 over the determinant, like I said. So that's going to be y1, y2 prime minus y1 prime, y2, and then the inverse matrix, which is y2 prime up here, y1 down here, and then negative y2, and then negative y1 prime, and then multiplied into 0, f of x over p naught of x. Nice. And then finally we can perform matrix vector arithmetic here. So we can take this determinant out. I'll maybe write this as 1 over the Wronskian of y1, y2, just to keep it shorter, keeping in mind that the Wronskian is this determinant. And then let's see what we have for the matrix. So here we'll have minus y2 times f of x over p0 of x. So that's my top entry, just from taking this first row, swiveling it into this column. And then for the next bit, I'll have y1 f of x times p over p0 of x, I should say. Okay, so in the end, we can equate the entries. And notice that z1 prime will be 1 over the Wronskian times this function right there, described by minus y2 f of x over p0 of x. And then z2 prime is described by, again, 1 over the Wronskian and then y1 times f of x over p0 of x. But that's z1 prime and z2 prime. In order to find z1 and z2, we just take the antiderivatives of those two equations. Okay, so let's maybe summarize that over here, and then we'll have some examples. Okay, as a summary for what we've done so far, let's look at the following rule. And so that says that given a fundamental set of solutions, y1, y2, to this brown boxed homogeneous equation that we've been working with, then a particular solution to this non-homogeneous equation that we've been working with is of the form, well, we'll call it yp, which is z1y1 plus z2y2, where z1 and z2 are described by the following integrals, which we derived all of this on the last board. So this z1 is the antiderivative of minus y2 times f of x over p0 of x times y1 y2 prime minus y1 prime y2. That's the Wronskian. And then z2 is almost exactly the same, but instead of having a negative y2 here, we just have a y1 here. Let's recall that y1 and y2 are functions. That's why it makes sense to take the derivative here. Also, they are known functions. Okay, so let's do a couple of examples. We'll start with this one. We'll solve y double prime plus y equals secant x. And this differential equation is perfectly suited to this method because we can get our hands on the solutions to the associated homogeneous equation pretty easily. So let's recall that if we have y double prime plus y equals 0, then that means that yh equals c1 cosine of x plus c2 times sine of x. That's because the associated polynomial equation here is r squared plus 1 equals 0, which has roots plus and minus I, and this follows like some work that we did previously. We saw this earlier. Okay, so let's maybe brown box that so we have it. And while we're at it, let's call cosine y1 and we'll call sine y2. Okay, another thing that I'll do is I'll calculate the Wronskian. So the Wronskian of sine and cosine, recall that that is the determinant of the matrix that gives us this. I'm going to write it as the determinant of the matrix because it's visually easier to look at. So we'll have the functions in the first row, so cosine and sine, and we'll have their derivatives in the second row. So that'll be minus sine x times cosine of x. But the beautiful thing about this is if we take the determinant, we get cosine squared minus negative sine squared, which is cosine squared plus sine squared, which is 1. So the Wronskian in this case is 1. And let's recall, let's maybe put this in here. This guy right here, I'll put this in orange parentheses. This is the Wronskian. And that's also over here in orange parentheses. So we could write W down there if we wanted to. Okay, so now we're pretty much ready. So notice that z1 will be equal to the antiderivative of, so we need negative y2. So that's going to be minus sine x times f of x. So that's going to be secant of x. And then it's going to be over p0. But notice p0 is 1 because that's the coefficient of y double prime. So that's nice. And then this Wronskian, which is also 1. So we have all of that's just over 1, and then dx. Next up, let's recall that secant is 1 over cosine of x. So this gives us negative the antiderivative of sine of x over cosine of x, which is the tangent of x. Now that's a standard antiderivative, which you probably know from an integral calculus class. That'll give us the natural log of cosine of x. So notice taking the derivative of the natural log, that'll send cosine into the denominator like this. And then we'll have the derivative of cosine in the numerator that is negative sine. And you might say, well, what about a plus constant here? But we don't need to do that here because that's all wrapped up in our homogeneous solution right here. Okay, nice. So now let's calculate z2. So that'll be the antiderivative of y1. Notice that y1 is cosine of x times secant of x. again over 1. But cosine of x times secant of x is just the number 1, so that gives us the antiderivative dx or x. So here we've got our z1 and our z2. Now we can put this together into the general form of our particular solution. So it's going to be z1 times y1, so that'll be cos x times natural log of cos x, plus z2 times y2, so that'll be plus x times sine x. So there's our particular solution. And if we wanted to put this all together, our most general solution would have the homogeneous part and the particular part. So we'd have c1 cos x plus c2 sine x for the homogeneous solution, and then plus cosine of x times the natural log of cosine of x, and then plus x sine x. So that would be our final solution in all its glory. Okay, let's do another one. So for my next example, we're going to look at the differential equation y double prime plus 3y prime plus 2y equals 1 over 1 plus e to the x. And since we've got just constant coefficients here, it should be fairly straightforward to find the homogeneous solution, so we haven't been given that. So we'll have to find that on our own. But if this were more complicated, maybe the homogeneous solution would be given to you. I've got one of those set up for a warm-up. Okay, so let's look at the corresponding homogeneous solution, or homogeneous equation. That'll be y double prime plus 3y prime plus 2y equals 0. So we need to look at the polynomial equation, which is r squared plus 3r plus 2 equals 0, which factors as r plus 2 times r plus 3 equals 0, giving us roots -2 and -3. So using everything that we know about these types of differential equations, we know the general form of the homogeneous solution is c1 times e to the minus 2x plus c2 times e to the minus 3x. And we might as well call this first one y1 and this second one y2. Okay, great. Now let's calculate the Wronskian because, you know, that's of use here. So let's calculate the Wronskian. So that's going to be the determinant of the matrix formed by y1, y2, and their derivatives. I'll read it row-wise. So we'll have the functions in the first row. So that'll be e to the minus 2x, e to the minus 3x. And then their derivatives in the second row. So that'll be minus 2 e to the minus 2x and minus 3 e to the minus 3x. So what do we get when we take that determinant? So we'll get -3 e to the minus 5x from this, and then minus a -2 e to the minus 5x. So that all adds up to negative e to the minus 5x. So that's our Wronskian in this case. That's the thing that's going to show up in these denominators. Okay, so now we're ready to calculate our particular solution. We need z1 and z2. So z1 will be the antiderivative of negative y2. So let's see, that's going to be negative e to the minus 3x. And then we're going to multiply that into the forcing function. That'll be 1 over 1 plus e to the x from this rule right here. And then this is all over the Wronskian times the function which is multiplying y double prime, which in this case is 1 again. So we have negative e to the minus 5x. So we're working with something like this at the moment. Okay. So let's see what this turns into. So these two minus signs will cancel. We can flip this e to the minus 5x up, and that'll give us e to the 2x. But looking ahead, I'm going to write that as e to the x times e to the x dx. Just keep in mind that comes from me moving this e to the minus 5x up, and it turns into e to the 5x. Combined with this one gives us e to the 2x. And then in our denominator is 1 plus e to the x. And now this antiderivative is perfectly set up for u substitution. So let's say that e to the x was u, then we have a u in the numerator and the denominator, and then the derivative will be e to the x du. So there's our du. So let's put that over here. We're setting u equal to e to the x. That means du is equal to e to the x dx, just by taking derivatives. Okay, so that's going to give us something like this. So we'll have u over 1 plus u du. But how do we solve something like that? Well, that's a rational function. We've got the degree of the numerator is the same as the degree of the denominator, so there's a little bit to work with. So maybe I'll add 1, so plus 1, and then I'll subtract 1 as well, just to make everything work out. So we can split this 1 plus u over 1 plus u gives us 1. And then minus 1 over 1 plus u du, and now we know how to take the antiderivatives of those portions. That'll leave us with u minus the natural log of 1 plus u. And I'm playing it fast and loose with not needing absolute values, mostly because here I notice that u will be e to the x, which is never negative. Okay, so plugging this back in, we'll see that we have e to the x minus the natural log of 1 plus e to the x. So that is my z1. Okay, so let's bring that here and then we'll calculate z2. So we just determined that for this problem, the function playing the role of z1 is e to the x plus the natural log of 1 plus e to the x. So now let's calculate the function playing the role of z2. So let's see, we need y1 times f of x. y1 is e to the minus 2x, so that's going to give us e to the minus 2x times 1 over 1 plus e to the x. That's all within an antiderivative. So that's our numerator. Now our denominator is the same thing that we had before, which was minus e to the minus 5x. So minus e to the minus 5x dx. Okay, so let's flip that up again. And that'll give us the antiderivative of, maybe I'll bring that minus sign out, and I'll have e to the 2x times e to the x dx over 1 plus e to the x. After moving some things around, keeping in mind that we're going to have a similar substitution that we had on the last board. So notice this flips up and now gives us an e to the 3x. I saved it like that because, again, we're going to have a similar substitution. So let's write the substitution over here. We'll have u is e to the x, du will be e to the x dx. So notice we've got a u here, we've got a du here, and this will be u squared. Okay, nice. So this is going to give us negative the antiderivative of u squared du over 1 plus u. Something like that. Now from here, unfortunately, we're going to have to do polynomial long division to simplify this a little bit. So let's write this as 1 plus u dividing into u squared. So we'll start with a quotient of u. That'll give us u squared plus u. So that we'll group and subtract. That'll give us a negative u. So that means we need a minus 1 here. That'll give us minus u minus 1. And notice we'll have a remainder of 1. So I went through that quickly, but make sure to review polynomial long division if you haven't done that already. Okay, so what all that means is that we can write this as negative, and then we'll have this quotient, which is, like I said, u minus 1, and then plus the remainder over the divisor. And so that'll be plus 1 over 1 plus u, and then we'll have du. Now we can take this antiderivative fairly easily. That'll give us u squared over 2. And then we'll have plus u, and then we'll have minus the natural log of 1 plus u. Now plugging in back e to the x, that'll give us 1/2 e to the 2x, because that's u squared. And then that should have a minus sign out front. And then we'll have plus e to the x, and then minus the natural log of 1 plus e to the x. Great, so now let's bring that up right below the z1, and then we'll write down our final solution. So this is where we left ourselves off with Z1 and Z2, and now we're ready to put it all together. So our final solution, y, will have our homogeneous part, so that'll be C1 e to the minus 2x plus C2 e to the minus 3x plus Z1 times Y1 following this format. So that'll be e to the x plus natural log of 1 plus e to the x times, like I said, y1, which is e to the minus 2x, and then plus z2 times y2. So maybe I'll factor a minus sign out because more of these have minuses than not. So that'll be minus, and then we'll have a half e to the 2x plus e to the x minus natural log of 1 plus e to the x. Sorry, I messed up my signs there, and that'll be all times e to the minus 3x. Okay, so now let's start putting this together. So we'll have this is equal to C1 e to the minus 2x plus C2 e to the minus 3x. That's our homogeneous part. And then let's see, we'll have e to the x times e to the minus 2x. That'll be e to the minus x. And then notice here we've got a minus half e to the minus x, kind of for the same reason. So those add up to plus 1/2 e to the minus x. And then we've got this e to the x times e to the 3x, which gives us e to the negative 2x, but we can just absorb that in right here just by replacing C1 with like C1 plus 1 or C1 minus 1 as needed. So just to reiterate what happened, notice that this term right here times this term right here will give us a homogeneous solution, so we can absorb it into the homogeneous solution. Okay, so left over is the stuff involving the natural log. So we might as well factor that out. So that's going to give us plus e to the minus 2x minus e to the minus 3x times the natural log of 1 plus e to the x. And that would be a nice final format for our answer. Okay, so I'll end by giving you guys some warm-up problems. I'll leave you with 2 warm-up problems. So the first is one that's built so that you can find the associated homogeneous solution, and that is y double prime minus 2 times y prime plus y equals 14 times x to the 3/2 times e to the x. Then the next one is not built so that you can easily find the homogeneous solution, so I've given them to you. And that's x squared times y double prime plus x times y prime minus y equals 2x squared plus 2. And then the homogeneous solution can be built by the following 2 functions. So we've got y1 equals x and y2 equals 1 over x. And that's a good place to stop.